My name is David Talbot. This is Claudio Bauer. We are both from Teacher, so a startup software company, a couple of here in Bellevue. What we built is a sort of platform called xPatterns, which is a vertically integrated big data stack. So if you're looking to build a large recommendation system, anti-fraud system, prediction system, you can build from scratch. It includes everything in the infrastructure layer. So we do Spark, chart, methods, dealing with streaming data, everything we need there. We do the advanced analytic bits, specialties around machine learning, text mining, inference, and simulation programs. And we also do the top-end serving application layer, where you need to be able to push both amounts of data, as well as any models that you build, like so recommenders, classifiers, whatever the case, to front-end servers on which you build custom-facing applications. So we deal a lot with the integration of all those pieces. Cassandra fits in. Cassandra basically is our go-to NoSQL for the serving layer. We need to serve data. Okay, so for example, we do a lot of work in healthcare. So let's say we have 200 million patients. We go the information, and we do a lot of backend processing around risk prediction, around population management, around fraud. Then we build the front-end application where you have any patient, you need to have the 10-20 millisecond response time and be able to show correct statements. The really fastest solution is to use a NoSQL database and publish data there. And then it also gives you a nice separation between your analytics store, where you're based on HDFS partner mostly, and your serving layer, and you can have separate SLAs and separate resource scalability for those. Another here, so that's all platforms. One of the other things we do, and which we did, we did in Cassandra with other pieces. We don't just build the reference architecture and then whenever a new project comes, we implement it. We try to go in and automate away most of the learnings. Right? We say we build the platform, so the goal is really to come and say, everything we learned over the past 3 years about Cassandra, which is all of which depends on it on a very fundamental basis. In terms of how you do data modeling, how you do security, how you do throttling, how you do geo-failover, how you really implement it in an enterprise environment. The goal was to come and say, okay, can we automate it when we get to a point where it's a checkbox, it's a drag and drop thing, and then in the backend, we take all of the design patterns, the best practices we've learned, and just build them into the toolset. And that's what the platform, so you can see those capabilities and tools, but basically the specific roles people that you build tools for. And the goal is really to get to a point where if you build an application, you should know as little as possible about that technology to make an application up and running. This is a fairly typical deployment we would have. And it's in basically there are two layers here. One layer is basically an analytical store. So for us, the normally the HDFS, Spark, chart, and Nessus for resource management, and the other result, and Spark toolset on top of that. And that's where data would fit in, and that's where data scientists would work, and that's where some field with data quality workflow, the full ones, or the deltas we run. And we can keep this geo-replicated. We have some tools to do encryption and some geo-failover on the data. But when you are ready to build an application, what you need to do is you need to publish the data with publish of some workflows and how the publish process actually works. So we publish it to a front-end Cassandra store. Okay, and that obviously requires to deal with things like the data modeling aspect, which we try to automate in ways as much as possible. Things like throttling, right? So now I have real-time customer workflow here, and now I need to update 20 terabytes. How do I do that in a reasonable way? security aspect, one of the other things we have to deal with was geo-replication. Specifically for us, we do a lot of work with highly regulated industries. So healthcare, finance, government. So you need to look at things like node-to-node encryption, dedication, how to just move stuff around in a sense. And then in front of these clusters, the rings, you have the servers, and clearly when someone writes an application here, so whether it's a web application or a mobile application, you basically just want to interact with the REST APIs, right? With some cache, you just want Cassandra. One of the other things we do is we just been able to automate away basically publishing those APIs. Right, so you find the backend, I try the data set documents here, and so okay, now I want to expose this, the person or whatever my document, like the Cassandra document happens to be. So okay, here's what I want you to send out, and then here's the set of APIs, the application you need on top of it. Here.
Our friends at Amazon that told us president this morning, and networking is very fickle. But this has put a lot of all our resilience features to a real test. Unfortunately, it comes on the day of the
Yes. So everything. So we wanted to show the actual geo failover, but now we actually have failovers. So it was the one-sided thing.
So being theoretical mode for a good one today is fine. So this is the HTFS NoSQL tool. And I'll do a quick demo of that. What we do is we connect the warehouse to Cassandra, and we want to be able to map data between the two systems and build an efficient data modeling process. Imagine you have 10 billion records in a warehouse, whether it's coming in type or short, doesn't matter. If you want to map that to 10 billion rows in Cassandra, you're not going to get the advertised performance capability. So what we do is, literally the 10 billion records in the warehouse, we're going to map that to a maximum of 50,000 rows in Cassandra. So we're going to build wide rows, but we'll see in the lesson learned slide, how we pick that size, how wide are those rows, not too wide, not too skinny, so that we have this, the output performance. I'll show you the demo first, and then we'll talk about the details. Implementation is behind the scene. So I'll create a demo, I'll select my database. This is a demo, it's a demo of the quantum. With 4 nodes, beefy nodes, 32 cores each, 60 gigs of RAM. Database. This is slower than I've ever seen.
That's because it's a demo.
So if you ever want to know when AWS failed, just see when a teacher is at conferences.
Always works in lessons and demos.
Okay. So at least I'll show you what previous run is. Unfortunately, I cannot do this live if we don't have time. But basically, I picked the database in a table in the warehouse. And now I was able to create a mapping before. The mapping means showing how many fields we want to track over. And maybe some data transformation. Converting from string to base, creating a unique key. In this case, I created 2 mappings, NPI partial and NPI full. With NPI full, I'm transferring the entire data set, creating 100 fields. But maybe I'll have some APIs that really don't require outputting the entire data set. It's just need a number of files to use for that. So for the sake of the demo, I created 2 mappings, full, which transfers all the fields, and partial. From partial, I will create 2 APIs. And this is where the application engineer comes in and defines what data do I need to read and how. So they define what we call the read access pattern. They specify a REST API method. They define the lookup fields, out of the field that they selected, in this case name. And what they get at the end of the job is a published URL. And this is the endpoint of the URL. This RESTful endpoint has three big attributes. It's geo-replicated, like it's on the diagram. It's monitored and instrumented. I'm going to show you how that works. So then, as we know with NoSQL, we heavily normalize data, so we create materialized views of our data sets, and we expose those for the most, in the most efficient way. So for the 4 APIs, we're pretty much creating 4 different data sets if you want to Cassandra, even though they're stored in the same one big compound. After we run the job, what we get is, while we run the job, we get the full log of what happened behind the scene. So we connect, we submit to a job server. We need Spark behind the scene to do the task. We create a special context, and we give it to the Mesos cluster. This is our Mesos cluster running all the Spark job server and the shard server. And you saw these contexts created. My job. We run the job and then we build the context. We're using the entire cluster as 128 cores, this much memory that you can figure. When you run, the important aspect is when you run a job, we're asking the patterns on level. We want to know how many cores, how many processes should we use on the Spark side for transmitting the Cassandra. If you have a mismatch there, for example, 100, this was Spark. Doesn't matter for that. We've done in the past, Spark nowadays. If you have 100 nodes against maybe a little Cassandra ring of 3 nodes, you're putting all those 100 nodes transfer data towards the Cassandra ring, you're very likely to choke at the Cassandra ring. It's not going to put on that much load. We'll start dropping calls, we'll start throwing exceptions. And that's important because that's part of the problem we're going to be implementing here. And we start with specifying maybe a very generous 1,000 cores. Now what we'll get back is whatever Mesos is able to give us, which is a maximum of 128 that we saw here. But even with that, especially if it's a big cluster, we might see problems. So if we run the job, we get the full log what happened behind the scene, execution details. We're sizing the data. Like we find that really that height table is backed by this HDFS file, which has this size. And that's very important to us because that's how we know how to split that data set into rows and columns. We know how wide the rows should be and how many columns should be created in one row and how many rows to create. This information is here is that critical. And then we read that data and we start transferring it over. We did some checks, checking for unique keys, for no values, doing the transformations. And at the end, we start the data export. Now we export to this is our key space platform data, and this is a dynamically created column family. This is what fails today in this cluster. Now we have all these resident features, but when we create a column family, we need to have all the nodes up because that they have to be propagated across all the nodes. And if they're not done in time, if they're not synced, creating a column family fails. It's something probably people don't do very often. You create a column family once and then you just access. You really have idea. But since we're creating the dynamically, we're seeing this effect. At the end, in the process of transferring, we have these dashboards that show us the total license rate and calls throughput. So that shows you how each Spark node performs. And this will give you an idea of how each Spark node performs. And going through the retry count, which is a special metric which doesn't show up now. Because the Spark node is too small for the Cassandra ring. It's only 4 nodes against 3 Cassandra ring nodes. And we have a very efficient way of writing data, so we're not putting enough stress on Cassandra. If we put enough stress on Cassandra, like let's say we have 1,000 or less than that, probably with 100 Spark nodes, we already see this effect. You see the retry count popping up here. And you see that will tell you that maybe you're over-generous with that parallelism level. And then you'd be able to stop the job, go back and reset that parallelism level, add less. Now in the future we want to do this auto-throttling automatically, so we don't have to, we don't require the application engineer to have that kind of knowledge.
Do you have to go there a way to actually look through and visualize the Cassandra cluster? You have to go build it all ground up, or is there any UI or tool available outside to find it?
That's a good question. We already told Cassandra, all we have is CLIs. There's nothing, and we build APIs on top of Cassandra. We did all the data modeling behind. We have this tool in PHP, it's open source. But it's just used for reading on the modules to read data out of it. You might have seen it. But we don't rely on this. We do a lot of operations with the CLIs. And the point to mention is we use Hector, we'll be using Cassandra since 06, so we haven't switched to the new practice yet. At the end of the job, you see these publish endpoints. Services.xpattern.com, and you can pick one up from here. And then maybe it's tested, and I'm using personally to test it out. Pick any NPI, let's pick an NPI from related party. So let's test it out. Let's see if really, we go back to the warehouse. That's our tool we built on top of the warehouse. I'm going to go to the table that I actually exported. It's called NPI-all. I'm going to run the query quickly. This runs on top of Spark and Sharp.
Sorry, what did you say there? It's on top of what?
On top of Spark and Sharp. That's in our warehouse. So I'm going to pick just one random API from here. You see my API now facing exposing data in Cassandra, it's actually working. It's better than working. Good. So that's our API now. Now the fact that I'm talking to server.xpattern.com means this is geo-replicated endpoint. If I want to add 5.0, this will actually only work against the East Coast cluster. How do I verify that? So I mentioned that APIs, we have instrument and modules. So we have something called modules that's showing, that's monitoring and just monitoring our clusters. And I'm going to go to my West Coast front and West cluster to see if we actually have those showing up. So we have external API metrics alongside others like this network CPU and Hector metrics. Everything that Hector exposes about the Cassandra name, the host. We have all these alerts set up here to notify us when things go down or servers are not performing. So we have based on API metrics, and I'm seeing my read data. That's my generated API. It's the number of calls, average latency, exception, throughput, and so forth. So this is what you get out of the box by using this tool. Again, in one, just to rehearse that, usually it would take us 9 weeks to build all this for each solution, for each application. Understand Hadoop or Spark, know how to write a transfer job, map reduce or Spark job, move it over to Cassandra, build a very efficient data model process, build APIs on top of that with resilience features, with instrumentation, with all the ingredients that we need to have for the enterprise class APIs that we're publishing, do the deployment, and so forth. So that would take people to do that, usually a 2-man or 4-man team squad. And now with this tool, we allow this to run interactively from the GUI. So there's a lot of power, a lot of things we still have to add in the design the mapping. This decides to work. We only had lookup, key, and sort. We want to add group by and filter, which are a lot more difficult to do in NetSQL, right? It requires more generalization, more model. Any questions about the tool? Now I'll switch back to the slides. I'm going to get to lesson learned. How much time do we have? Couple of minutes, okay. There's a lot more information in the slides. We'll share that so you can read it. If you're signing up for Cassandra Summit, we'll have a much longer session there. We'll go into a lot more details about everything we did. Cassandra, so make sure you catch that. Lesson learned 06 and 206, what we have today, is a lot of the issues were fixed in the meantime, but the one big thing, and I'll focus on this, is custom serialization and dynamic columns for maximum performing team. This is what allowed us to get 40% improvement. Instead of storing each column, each field in a database as a separate column in a row, now we're actually doing our own serialization on the client side, storing that one entity, whatever object you want to say, one big blob. You're just storing the blob.
I using protocol for that.
I don't know what custom serialization for that. Yeah. It just works with all the entities that we have. So we cut down on any metadata source or whatever any serialization engine.
What's the default serializer in Cassandra? Right. What's the default serializer on Cassandra?
What's the default?
Serializer.
Oh, no, we store this binary as a block, and then we give it to Hector.
Yeah,
Store it with it.
that's what you built.
Yeah.
What is the default?
Well, I don't know. I know that we deal with compression that we use for compression, but I know they have their own trips the initial drive. I'm not sure what the new ones are doing, but probably something similar. But doing your own custom serialization will always beat any other generic serialization engine because you know exactly what you need to store and how. And what works for us consistent level of 1. That's because our use case allows to do that. Don't be afraid of them. I know people come from the SQL world and still nervous about PHP consistent level 1. But what it means is even if you have a node failing, the writes will be replicated in time. If you don't do the reads, you really have to write. You shouldn't be concerned about it. Right? In our use case, we would capture all the data overnight and have all the read operations done before during the day. Dashboards are always read-only. The only reading data of Cassandra APIs. The writes are happening behind the scene from our warehouse. So, Cassandra 1 also gives you a very good performance improvement. About the data model, rows not too skinny, not too wide, right? In order to avoid out-of-memory, especially in high throughput write scenarios, we would see that a lot. When we optimized the data model and we started doing serialization, and we started splitting again, that's 10 million records in the warehouse, moved maybe to 50,000 rows maximum in Cassandra. We put a lot less stress on Cassandra.
I think it's important to make this distinction. You're talking about wide rows, whereas which is like really kind of the old terminology. Just so everyone's clear, he's talking about wide rows. That's a partition with a lot of rows inside. Like when you say rows your way, you're thinking about it from the old Thrift API.
Yeah.
Which if you read the documentation, it's not used anymore, and it might be confusing for some people.
So what's it called now?
Now you call it a partition.
Okay.
Like it's a CQL partition has a single key and multiple rows inside that key. Just so everyone is clear.
Okay. So this is a partition. But it still consists of columns. We use composite columns there to do all the reads. So we never actually read the entire row in order to get to our one object that we need to isolate the APIs. We do slicing. And that's critical. And the reason that here why we do that, reducing network I/O, less rows means more common slices, means that they're more efficient compaction. The key cache and the root of the sizes are lower, and just in general less memory pressure in nodes. The second point here is reducing the number of column families. That's been critical until 1.0, I believe. We had to really cram all the rows. In the end, in NoSQL, you don't have to have different column families for different data sets. You can store any row, right? There's no constraint on what kind of rows you have. So if your application knows how to read those rows, they can mix multiple rows, row types in the same column family. And this is what we try to do to reduce number of column families. We're trying to do multiple data sets in the same column family. Nowadays, there's a new setting called empty table space and anyways that somewhat take it a little bit, but I haven't tested that extensively to know whether it's still an issue or not. Like I said, some of the issues have been fixed since 06. We weren't able to regress everything. It didn't happen. And I still consider these good practices. That's it. Questions?
On the throttling Spark nodes, because Cassandra writes or potentially Cassandra was weren't seeing. There was never a case where the reads from HDFS you had to slow things down to that.
No, because when you have such a big cluster, the network between Spark and Cassandra becomes the one. Those nodes can read at their own pace, so you need to have data in memory. They're ready to send over the wire to Cassandra. So because the cluster is so big, all those nodes will have data in memory.
They already have
the HDFS like is good.
in memory.
And in the end, the Spark node they work against the open node, right? They don't have it expected. And if you look at these jobs, you'll get a lot of the details in the log, right? You'll get the Spark job details. So I'm going to look at the log here. You'll have to be issued the log to show at your time. But you have the Spark UI. In the Spark UI, you can look at your job and see if you have data locality. If the data locality is there in the UI, then you know that your next problem is sending the data from the Spark APM memory with a token or in the Spark APM to Cassandra. But when you have enough rows, you can saturate that network, and then your next problem will become Cassandra. The ability to adjust it.
So Spark and locality typically to HDFS.
Yes. That's a different system. We separate the two systems so we can monitor SLAs that predictable latency. We would never put Cassandra node and Spark in the same cluster. So in the end, this I/O is never managed properly. Even if we have the RMS nodes, we manage cores and memory, but never disks. Right? So this is always a shift model. So that's what we separate.
Okay, so overall, we've been doing this for 3 years now. So one is dealing with the same issues, and now we actually go and deal with the vertical integration very quickly. We actually take this in production, make this work in production, and always improve. Thanks.